Hi. So the first topic within the core section, right? We're going to develop on these values of distance, tie them up with velocity, acceleration, build some equations out, and hopefully you'll see how they're built out. You won't have to rote learn them. You should gather them intuitively. That's the goal. So we'll jump straight into it. And again, I'm going to cover a little more just beyond coming up with these equations. I'm going to build out some other ideas here because we also have force that comes in when we bring acceleration. We might have to think about momentum. We'll just bring all of these together here, and perhaps over 1, 2, or 3 videos, we'll understand how these things develop into slightly more solidified concepts in physics. I'm probably going to sacrifice on my colors just to make sure I don't spend too much time going and grabbing different chalks here. So I'm probably going to sacrifice on colors, but I'm going to assume you are very familiar with notations for mass here, cursive M, meters here for distance. Make sure you understand those and you're clear about them. Don't confuse them. Units are very important. So we'll jump right in and we'll start off with working on distance. We'll start with our velocity equation. I kind of like that, right? So we'll bring that velocity equation here and say velocity is distance over time, right? Now, let me just take that basic mathematics, right? So I would say distance is equal to velocity times time. Very intuitive. If you were traveling at 100 kilometers an hour passes, you've traveled for 100 kilometers. It is very intuitive, and I'll take this thing, I'll put it in a form I kind of enjoy, which is, I call it the graphical side of mathematics. And if I did this, and I had, say, time on this axis, and I had, say, velocity on this axis, this can be represented here at any given time t and a given velocity v. I could now say the area of this rectangle is effectively distance. And intuitively, if velocity was higher, larger, you were traveling faster, you'd have a taller rectangle, more area, so you cover more distance. Or if you were just traveling that same velocity for a greater amount of time, you'd have a wider rectangle, more area, more time covered, right? Hopefully you can connect that, the intuition behind this and how that translates graphically. All right, we've got this one here. We also know, remember we talked about initial velocity and final velocity. We also know acceleration is really change in velocity over time. Let's bring that here for a moment and say, well, we know acceleration is the change in velocity, and I'm going to use that change in velocity because we know initial and final velocity. I'm going to write that in the form of initial velocity, final velocity minus initial velocity divided by time. Right? I'm going to build this one out and just play with the math here. And I could argue, or rather build out from here, that the change in velocity is nothing but acceleration times time. Now, mind you, here, acceleration is constant during the time that has passed, right? So if it was an hour, well, it wouldn't be constantly accelerating for an hour, that would be really fast, but if it was, let's say, 10 seconds, you're maintaining your acceleration at 10 seconds at a constant. So every second you would increase your velocity by the same amount, and that would happen every subsequent second. That's constant acceleration, right? I can also use this formula and play with this to say, well, what's final velocity? Well, final velocity, if I know initial velocity, would just be initial velocity plus, if I know acceleration, times time. Quite intuitive. If I was at rest, then my final velocity would just be acceleration times time. if I had an initial velocity, say 10 kilometers an hour, I was accelerating at, let's say, another 10 kilometers this time per hour squared. And if I traveled for an hour, you could do the math here, you'd know what your acceleration would be and what your final velocity would be. So this is probably a box here. I like these formulae, all kind of handy. All right. Now let's get to an interesting scenario. So we know if we had a constant velocity, we've got this, which tells us distance is velocity times time. The moment we bring in acceleration, that means velocity is not constant, velocity is changing, but we did say that acceleration is going to be a constant. But what would we do to distance in the event that we were accelerating? Perhaps the real question would be, if I did have an intersection, and this is just an illustration of a street. I have a speed camera here. I'm at that intersection. I've slowed down. There's and let's see, that's me on my bike. Get a picture taken with a reading of, say, 10 kilometers an hour. I've passed the intersection. I've decided to speed up. I'm accelerating. And let's say I get somewhere else. There's another speed camera here. And that's me after a period of time. And let's say it's now 50 kilometers an hour. Obviously, the distance between these two is s. The time that's lapsed between the two speed readings is t. We know initial velocity. We know final velocity. How do we build an equation with this? And we can then say define what acceleration is, right? Acceleration is probably v minus u divided by t. We know that. We need to develop an equation that brings s and all of these factors together, right? And this is the work here. Let me attempt to do this in three different manners, with three different levels of mathematics. Okay. Should we keep this picture? I will take this out. So what's our goal? We want to tie s, we want to tie velocity, we want to tie acceleration and time. And we know there are parts of this. What if we said s and then we couldn't do that because this is assuming constant velocity. We couldn't bring this there. So now let's take this and look at it a little differently. So if you traveled initially, if you had an initial velocity of u, right, and you had a final velocity of v, I could argue that during that time t, when these were observed, I could argue that you had something called an average velocity. Average velocity, and I'm going to call it, just for the purposes of this illustration, with a little bar on top, okay? And that would just mean the average of two values. With me so far? In which case, could I then say, well, the average velocity I'm going to assume is the velocity is the mean velocity during that time t. So I could conveniently now say s is equal to the average velocity times time. Cool. Average velocity is nothing but initial velocity plus final velocity divided by 2 times time. Okay, still good. Final velocity is nothing but initial velocity times plus acceleration times time. So if I substitute that, I'm going to get u plus a t by 2 times t. I think you've guessed the math. You will arrive at s is equal to u t plus half a t squared. The box. All right. Constant acceleration, 2 points at 2 ends of time measurement, u and v. I think we're looking good. Looking good. We could conveniently say average velocity was here because acceleration was constant. Let's take this up to the graphical side. Let's take a look at what happens. All right, what's going on here? Let's see. Got that. Got that. I've got time here. I started with a u. I'm going to end with v. Ooh, okay. So that would have been if I was traveling at just u. But in reality, by the time I got to t, I was at this place here. That means my velocity went up constantly. It was not changing. Acceleration was constant. So if that was u and that is v, that distance is v minus u. If this is distance traveled at constant velocity, distance now could be the overall area of this section, which is the area of the rectangle plus the area of this triangle. Let's see how the math checks out there. Okay, so if I did s is equal to area of this rectangle, okay, I've got that covered, and the area of this triangle. Well, the area of a triangle, 1/2 base t, height v minus u. Aha, v minus u is at. And very easily, look at that. We are back. Graphic, very nice. All right, now for those who know some differentiation, some integration, or some calculus, let's play with this. Now you know, if I have y as a function of x, I have the idea of differentiating y with respect to x with me. If y was just a constant value k times x, its first derivative would simply be this constant value, right? It would just be, so here dy by, I'll write values for dy, would just be k. If y is equal to k times, let's say x squared, what would happen? You'd end up getting 2k, and then you just get x as when you do the derivative. So that's basic differentiation, right? Taking the first derivative, that's the idea. If I took the second derivative, that would mean differentiating this, which means x would go and I'd get 2k, right? I just want you to remember this. Hopefully you already know differentiation, but I thought this might just be a good refresher to know what a differential would be, right? So that is what it would yield. That is what dy by dx would yield, right? Let's now apply that to this. So here, that x is really time, right? Time is that independent variable. We know distance is a function of time. So I'm not going to say y equals f of x, I'm just writing y, which is distance, as a function of time x, right? It's like a y of x. We also know that its first derivative, if you will, is velocity, and we know that's also a function of time. Its second derivative, d square s by dt square, is nothing but dv by dt, and we know that as acceleration. But if you're with me with this, you know acceleration is constant. All right, let's see where we go with this. So if acceleration is a constant, what might be, or what do we need to compute the derivative of so that we get constant acceleration, right? So if and work with me here, if I was able to write velocity as acceleration is a constant, okay? Another constant value here is initial velocity, okay? Similar to that equation. Now, if I differentiated that, my result would be with respect to time, so dv by dt. So if I do dv by dt, initial velocity is constant, differential with respect to time, so you only have a, and that becomes 0 because the differential of constant is 0. So I just get that. Looking good so far. Now we need to come back one more level to s. So it's almost as if we're going to attempt to integrate this function here to get s. And let's try to rework that. So I'm going to take this out and say, well, wait a minute, if I built this out and try to integrate this, it could be ut, because the differential then will give you u. I have t here. If I integrate that, it should be t squared by 2. Remember, here I'm applying the integral. The constant a doesn't change. And I'm integrating velocity with respect to time, so I should get distance. Try the derivative. Derivative of t squared is 2t, 2 cancels out, so you get at. Derivative of ut is just u, because u is constant. There you go. Only for those of you who have done some calculus. Otherwise, we have the simpler parts. But I just wanted to make sure you see where the math comes in and the real method of calculating. So I didn't get to the specifics of differentiation and integration, but I thought I'd give you an overall idea, right? So we'll leave the first video here, and then we'll come back and we'll continue on core concepts 1. We'll build out this equation and see what we get from there, right? We'll see you soon.